In this video, we present PASCAL, a property graph schema visualizer. The aim of this project is to develop a graphical user interface called PASCAL to help users understand their property graph schema and apply HCI, visualization, and cognitive psychology theories to make the interface visually appealing and easy to use. When working with graph database management systems, property graph schemas define the database's fundamental structure, including nodes, relationships, and constraints. Past property graph schema studies, such as PG-Schema, have aimed to standardize the data definition language for graph databases with a flexible and extensible syntax. PG-Schema mainly consists of two parts, PG types and PG keys. PG types define the specification for the combination of labels and properties in node and relationship types. It also supports inheritance, which promotes reusability and maintainability of the schema. Furthermore, the open keyword can be used to indicate that the node or relationship type allows arbitrary additional labels or properties. PG keys, on the other hand, specify key and participation constraints in PG-Schema. Although PG-Schema is expressive and feature-rich, its syntax can be challenging for some untrained users to comprehend. To solve this problem, we present PASCAL GUI, a user-friendly interface for property graph schema visualization. Now, let's walk through the visualization of each PG-Schema feature in PASCAL. For node types, the base node types are represented by blue circles, while inherited node types are represented as light blue circles. Similarly, for relationship types, the base relationship types are represented by purple rectangles, while inherited relationship types are represented as light purple rectangles. Relationship arrows, represented as purple Bezier curves, are used to specify the source and target node types of a relationship type. Labels are represented as yellow pills, and properties are represented as color-coded circles. Constraints are represented as red pills. They are translated into natural language for easier interpretation. Lastly, the open keywords are represented as green circles with an unlock icon. Next, we will see how the HCI, visualization, and cognitive psychology theories are incorporated into PASCAL. Firstly, proximity, similarity, continuity, symmetry, and common fate and Gestalt principles are utilized to make the interface visually appealing. Proximity is evident as labels and constraints are positioned near their respective node or relationship type, with data type or property circles aligned along the node type circumference or relationship type's perimeter. Similarity is applied using uniform colors and shapes for different elements. Node types are all blue circles. Relationship types are all purple rectangles. Relationship endpoints are all purple arrows. Labels are all yellow pills. Constraints are all red pills. Data type and property circles are all circles and color-coded based on their data type. Node inheritances are all blue dotted arrows. Relationship inheritances are all purple dotted arrows. And open keywords are all green circles with an unlock icon. Continuity is maintained by positioning data type or property circles along the node or relationship's boundary and using Bezier curves for all arrows, ensuring a smooth visual flow. Symmetry is achieved by evenly spacing out data type or property circles around the node type circumference or relationship type's perimeter. Common fate is employed as labels, properties, and open keywords move with their associated nodes or relationship types. Schneiderman's golden rules are also incorporated into the GUI design to enhance user experience. When there is a parsing error, informative feedback is offered through error messages that explain parsing errors, and runtime errors are prevented by skipping the generation of invalid schema. Actions can be easily reversed thanks to the support for undo keyboard shortcuts in the schema editor. Finally, the design aims to reduce short-term memory load by providing a data type reference panel, eliminating the need for users to remember color coding for each data type. In addition to Gestalt and HCI principles, other visualization theories, such as visual hierarchy, usage of colors, and usability of icons, were also considered when designing the PASCAL GUI. Now, we will demonstrate how to navigate and use the PASCAL GUI for property graph schema visualization. PASCAL features two views, Visualizer View and Text View, with seamless navigation between them. The visualizer view of PASCAL includes the left and right panels. The left panel contains a real-time schema editor that accepts plaintext PG-Schema input. The right panel displays the property graph schema visualization of the provided PG-Schema input. Users can also freely resize the panels using this handle. On the other hand, the text view of PASCAL presents the schema editor in full screen. To populate the schema, users can either choose one of the 3 example schemas or load a schema file containing a valid PG-Schema syntax. To load a schema, click the Load Schema button on the navigation bar and select a text file from your computer. After the upload is done, click the Save button. This will populate the editor with the schema, and the property graph schema visualization will be displayed in the canvas. After loading the schema, users can use the schema editor to make direct modifications that automatically update the visual representation. Additionally, users can adjust the GUI's visualization, graph layout, and workspace settings in the Settings panel. Firstly, the Property Visualization mode can be set to Data Type mode, where the properties are grouped together by data types, Property mode, where each property are displayed individually, or Hidden mode, where all properties are hidden. Secondly, the Expression Visualization mode can be set to Tree View mode, where complex labels are presented by a tree view component, or Expression mode, where complex labels are presented by plain logic expression. For the graph layout settings, users can choose to enable or disable the auto layout functionality of PASCAL. If auto layout is enabled, the graph layout is recalculated automatically every time the plaintext PG schema is updated. If auto layout is disabled, the elements need to be manually positioned in the canvas by the user. Alternatively, users can click the Fix Layout button to fix the layout on demand. Lastly, for the workspace settings, users can toggle the visibility of the schema editor and the data type reference panel. In conclusion, PASCAL schema visualization can help graph database users with query formulation and schema comprehension tasks. Also, the use of HCI, visualization, and cognitive psychology theories in PASCAL is proven to be aesthetically pleasing and useful for most users.